All right, thanks everyone for sticking around. So I will just show a few cases that we are working on in the lab. And we are using Metabolomics and we are pulling it down on environmental studies and using it to detect emergent pollutants, or if something is going on with the metabolism in organisms. And there's a number of people that has been involved and supporting this work, and they have been mentioned here. So as I said, we are using metabolomics in an environmental context, and this could be, for instance, that we would like to have some vegetables, but sometimes people are using biocides to produce these plants that we can eat, and maybe the plants, they would hold back some of these pesticide residues, or maybe it's metabolites of pesticides. Maybe the pesticides are ending in the soil, and the bad pesticides are maybe converted by microorganisms to some more environmental friendly metabolites that are not so toxic to public, but also environmental health. Then we could be interested in these organisms and try to isolate them and put them into groundwater supplies. They could also end up in drinking water supplies, and then end up in cities' water supplies, where people are drinking the water, and then maybe there could be some issues with the metabolome of the people. Maybe there's endocrine disruption. Maybe the persons are carrying a large part of environmental pollutants, and this is what we call the exposome. Then there could also be animals in the environment that are being affected by these pesticides or biocides, for instance. We also produce a lot of waste, and somehow it ends up in the environment. Maybe it ends up in a river system where there's some tadpoles or fish or daphnia that are being affected. And then we can capture some of these animals, or we can do controlled animal studies where we are looking into the metabolome changes of the animals from drugs or pesticides or whatever. We also look into natural substances that are leaching into the environment, and involved in some work on wildlife exposomics. And then we have some fun people associated that would like to look into ancient material and decay processes in bones or brain decay. That's really interesting. So, but I have like kind of combined everything into this workflow where we have, maybe there's a pollution of some river water, and we do some sampling with some sampling devices. Then we do sample prep, and then we put it on a high-res mass spec platform, and we do some magic with, mostly we are using Compound Discover for some of our work, and then we also use some other tools. Then we get a lot of features, and we can compare different conditions and see changes in the composition of the samples. We could also have a shopping list. This is typically in environmental chemistry, we call that a suspects list. If authorities are approaching us and then ask, is that a substance in this environmental sample, then we will just try and pull this out of the data. And then we could, of course, archive, as we talked about this morning, the data, and then you could revisit it. And much of our work is going into papers, hopefully, but also in scientific reports for the authorities that are public. And we try to write these in English, so it's not in Danish only, which is a change from the classical through procedures in Denmark. So first of all, we use different platforms. We use GC Orbitrap system, LC Orbitrap, and ion exchange Orbitrap system. And it is quite known from the Metabolomics Society what kind of metabolites are being retained and can be detected on the different platforms. So we also did that with anthropogenic chemicals, try and map what the chemicals are being detected on the various platforms and if there was any systems. What it actually showed when we spiked nearly 1,000 compounds into a bottle of water showed that you have to use different platforms to capture the entire chemical space. And this is what we are doing. We are combining the different platforms to do a proper characterization. So I have one example here that Mulato has been working on a lot. So Mulato can answer all the details if I cannot answer them today. But Mulato, maybe just raise your hand so everyone knows where to go. So this is a fun exercise. The Danish EPA contacted us and asked, is there something in our river water systems that shouldn't be there? And then we collected a lot of samples from rivers in Denmark. This is Denmark if you are in doubt. But some of the sites we were taking samples from an entire river, like distributed over several kilometers. And we took water samples, I think 0.5 liter, added internal standards, isotopic labels, internal standards, and then we did some enrichment on a solid phase extraction cartridge. We got an extract out of this, and parts of the extract we would like to analyze for the chemicals on 2 different platforms here. And parts of it we would like to do this toxicity evaluation where you would take a fraction of the sample and you can expose it into an in vitro testing system. For instance, in this case, it's an estrogen and androgen receptor. We didn't do that toxicity evaluation part yet, but this can support the evidence down the road. Then we do the data analysis on the data, and we did some semi-quantification I can come back to. So one of the platforms we are using is an LCMS. It's running with a nanoflow system. So this is a conventional LC here, and this are the dimensions for the nanoflow system. And the advantage of doing that is that besides it giving you a lot of headaches because it will clog really easy, the advantage is that the flow rates are really low and you get a lot more in sensitivity of the final results. So for instance, the easy spray formation of the ions is much more efficient, and the droplets are forming it's starting at a later stage of the ion formation compared to conventional electrospray. And I think we were going to talk more about electrospray later on a bit later in an hour or so. This is a typical chromatogram you get out of this. This is a base peak chromatogram for a fish, where you get a lot of peaks and a lot of information. The other system we applied here is an anion exchange system, where you have this. This is the column, and then you have the flow path of your mobile phase here, and this is the stationary phase that is positively charged. Then you can have anion metabolites. In this case, it's symbolized by this nice protein that could stick to the column. And then you can add hydroxide as an eluent or increase the hydroxide concentration, and then the analyte of interest will elute. And then you will get, just like in LC, you get nice chromatographic peaks. And this is what we have done for a groundwater sample here, where we find trifluoroacetic acid. And this is a peak for formic acid, a cluster with sodium that generates this almost the same accurate mass. You can only distinguish these two molecules by the retention time difference in this system and the MS2 pattern. Then we went out to this river system around a small city in Denmark, I think with 40 or 50,000 inhabitants. And we collected samples from the west side of the city along a river. And then there was a river, small creek here running around agricultural areas. And then there's a firefighting exercise facility here and some hospitals, airstrips, and then butcheries to produce bacon in the city. So, which is interesting. There's several wastewater facilities around the city. Over here is also one. So then Molato developed this nice workflow that we are using. We are using a mix of Compound Discoverer and MZ Mine, and everything goes into GNPS and Cytoscape in the end. Molato is working on that at the moment. And then we are using different spectral databases to confirm the identity of the substances we find. We use Mass Bank, MZ Cloud, and some in-house libraries, ChemSpider, PubChem. And then then we are collaborating with a company that are doing semi-quantification. And then when we are measuring after we have acquired all the data, we are pulling it into this Compound Discoverer, and we get a long table of features. And we don't care what it is at this point. But when we do a PCA plot, it looks like this. Our pooled QC is here in the center and clusters nicely, which is good. This is what we want to see. There are some samples here and other samples in another cluster. There are some field blanks also, and a large sample out here. And now we want to identify, now we are using the different spectral libraries, and we want to find out which compounds it is. And after we have done that, we are pulling out only all the IDs. And then just to talk about the ID levels, we are also going to talk about that later. But within the Environmental Chemistry Society, there's 5 levels of identifications. And it's the same within the Metabolomics Society, there's 4. They follow each other more or less. But the level number 1 is the highest, where you confirm the metabolite or the standard or the molecule by buying a reference standard, and you inject it on the platform and you confirm it with MS1, MS2 retention time information. Then there's level 2, it's also the same. You get the spectral data, MS1 and MS2. You compare that to a library that are public available. And we are only reporting level 1 and level 2 data. And you should be very clear about when you report something, is it level 4 or is it level 3 or is it level 2 or 1 in your studies. Then we take that information and we try to quantify the abundance of the molecules. And we do that with semi-quantification methods that has been published by others. And so we added 17 internal standards. And if you can see these colored peaks in the background, that's the internal standards. And we feed that into this algorithm that it contains certain moieties in the molecules, and from that it predicts the concentrations of the unknown molecules. So we know how much we've added of the internal standards, and from that we can calculate the concentrations of the unknowns. And then we find out concentrations of, for instance, some atrazine pesticides and what concentration range they are in the river water, and how many samples they are detected in. And in the end, we are ending up with something like 40 substances that we have annotated at the highest level. And when we do this PCA plot of this, then we can see that some substances that are pesticide-like, they are highly associated with a sample from the agricultural area, this M30 here. And there's some samples are associated with pharmaceuticals and so on. So from the same data set, when we presented this, the authorities are very interested in it, of course, but they also found some reports on that was published recently about some chemicals that are being used in tire production for cars, and this substance that are being used as an additive in tire production, that's not so good if you are a salmon or a trout living in rivers near roads, because it has been found out that the lethal concentration of this substance is around 95 nanograms per liter. So they ask, is this substance in our river waters, and what's the concentration and so on. So several months later, we went back into the data and pulling out this mass, looking into the MS2, and we can see that there's a certain fragmentation pattern that matches with the fragments that has been used for targeted analysis in this paper with the coho salmon. And we also did some in silico fragmentation. In this case, it's medfrag, and it matches with the fragments that we have. So we could say that this is a level 2 substance, and it's highly likely present in the sample, and we could quantify it. It was not around 95 nanograms per liter locally, so there's still trouts in the rivers. Then we use sludge from wastewater facilities. We use that also as a fertilizer on agricultural soils, which is very good because it contains a lot of nutrients. But guess what? It contains also a lot of other stuff. So we used GC Orbitrap and LC-MS for this, and we used some pressurized liquid extraction techniques to do that. And when we did that, we found like, I don't know, thousands of substances. We could only identify a few % of them. And we could see some clear distinguished profile between the different sludge sites, the different wastewater facilities. So we also tried to do this differential analysis between two sites in this case, where you look at the log fold change between two sites and the minus log 10 p-value. So the higher up here on the y-axis, the more significant, And the longer out on the sides, the more change in concentration it is. So in this case, there's a dot here, and every dot is a metabolite or a xenobiotic. So in this case, this dot here is in very high concentration in sample A or site A compared to E. And if we go deeper into the data, we could annotate this substance as a pesticide. And then we have provided the Danish Ministry with a long list of chemicals. And we are also at the moment extracting fluorinated substances out of the data. Yeah, and by that, I think I will stop showing some cases, but I can show you a more data in the week if needed. But yeah, and I will take any questions. Yeah.
I'll start the questions again. I think it's very interesting, but I think one of the problems with the targeted analysis is quantification. You said that you use like 17 internal standards, and then you quantified basically almost everything that you could identify. How do you, there must be some general rules on how you decide which internal standard to use for which quantification? Is it just by retention time, or by the chemical structure, or by how do you?
Yeah, it's a good question. It's a mix of using retention time and structure that is fed into this model, and then it's a machine learning model that just takes all the data and are processing it.
So you tell it with this, you look at what you have annotated, and then you say for compound X, I want you to use standard 16, and for compound Y, it's standard 13.
Yeah, you don't do anything. You just feed in all of the data, smile codes, and then you have a smile code for an internal standard, and then you say it's 10 nanograms per liter for that, and then it predicts. And of course, there's uncertainties. At the moment, I think we are operating at the scale of a factor of 10 or something like that on these models, and it's getting better and better. Of course, if you add more internal standards, it would be much better. Yeah.
Could you use one of the internal standards as ground truths and the test?
As what?
As ground truths. So if you would say, okay, let's only consider my 9 out of 10 internal standards, and like the 10th one, I feed it in as unknown. How does it perform that?
Yeah. So we are also at the moment we are some of the substances are at level 1. So that means we have a reference standard. So we can also run our own calibration curve and check that. And that is, Molato, how is it going with that word? So
the way checking whether they are giving the same or the outcomes align or not, still I'm working, but so it seems that they are somehow related.
Yeah.
And comparing the trace finder data and the semi-quant data to different.
And the real advantage of the semi-quant is actually just to apply it on level 2 and level 3 data, because you could do the quantification on your level 1 already yourself. It takes a longer time, but and then you can also feed that into the model.
I mean, the problem will be that you can only do external calibration, or you have to rerun all the samples, right?
Yeah.
So then, like, think about ion suppression. There might be other factors that feed in.
Yeah.
There was one slide where you showed the concentration range. That was the uncertainty interval, or the minimum max that you observed.
That was the minimum and max between the 38 samples, I think. So there's some pretty high ranges there. Yeah. Yeah. Cool. Other questions? Yeah.
different MS to cover the whole chemical space, but how about the like sample treatment? And so because for these different compounds, like loss and recovery during pre-treatment can also vary. I assume you may use the solid phase extraction to concentrate the sample.
Yeah.
Yes, then even the different column can also lead to a different recovery of a range of different compounds.
Yeah, it's a very good point that that how we do sample prep and how are we sure that we can capture everything. Well, there's no method that can capture everything. So so we are just like trying to capture as much as possible. We do a basic, like a fundamental solid phase extraction, and then we close our eyes and then we capture what we capture. But we have shown with spiking 967 substances, we capture 70% of them by doing this. And these substances are wide ranging from small molecules, really small, to large ones, like DDT and fluorinated compounds. So,
which ones do you not capture?
I think there's some very low molecular weight substances that are problematic in drinking water supplies, and there's also some other problems with Orbitrap systems in that connection. We cannot go that low in scan range. So there you really need to take the raw water sample and maybe evaporate the water or just inject the water directly. And I think this ion exchange system is a very interesting system for those molecules that are very mobile in the environment and contaminating drinking water supplies.
I have one question. It might be off topic. We can actually discuss more of it later, but I'm actually curious about data storage in general because we produce a lot of data, and does the unit supply a lot of data storage in general, or is there any problem with data storage in general?
Yeah, it's a good question on data storage. So we are involved in European Union projects. So we are required to store data for 7 years after the project ends. So we have a deep freeze storage of where you put it into a tape station, basically, but it's a network storage that the university has, where you can only pull data or copy data to that drive, and it cannot be deleted for 7 years. We have solutions like that. And then we have cold storage where it's accessible like within seconds, all the data. And there we have all the data also, and are processing data directly on network drives. So there's eight copies of the data or something like that. Yeah.